In this course, we introduce the basic of stochastic processes. What are stochastic processes? A stochastic process is a collection of random variables that models a phenomenon that appears to evolve randomly. Let's make an example. Here we have three stoves that are very similar, and we have gas that is making a sound. And let's play the sound of the three stoves in sequence. This is the first, this is the second, and this is the third. Well, if you remember, the three sounds seems very similar to you. But if you look at a piece of the three sounds, you see that the temporal evolution is really different. This is because these signals are random, but they have common statistic properties. Each of these signals is a realization, and the process is the ensemble of all the realization. So to better understand the concept, let us consider another case of a process in which we can have a mathematical model. The mathematical model describes the process that is a spring that is subject to two forces. One is the gravity, the acceleration, and the other is the compression. So you can write the balance of the two forces. You end in a differential equation, and the solution of the differential equation is this, in which you can say that in all these three realizations, the period, the frequencies of oscillation is the same, and also the amplitude, the excursion is the same. But what changes in the three realizations is the initial origin, so the shift. So these realizations are sinusoid, but sinusoid shifted by a random variable that is phi. So also this is a process, and there is a stochastic variable inside. These are random processes, and how we can characterize statistically? Well, first of all, let us consider first-order statistics. What are first-order statistics? Let us consider some realization. In principle, this number of rows should be infinite, but here we draw only some of this realization. And let us point the finger in one precise position, so at a precise time, and say what is the statistic properties that we read along the realization. So what is the mean of this value? And we can compute it and find that it's 0. What is the standard deviation of this value? And we can compute it mathematically and say this is value. And we can also compute the probability distribution of all this number. I repeat, read only along a column. Okay. So these are the first order statistics. But if you look at the statistics, you see that none of these depend on the real position where I point the finger. So this means that if I consider the statistics read over the vertical direction in red, or at a different time in green, or at a different time in blue, and for example, I compute the histogram, I see that three histograms are really very similar. They are not exactly the same just because the process is made of limited realization. But if I would add infinite realization to this process, I would have this probability distribution function. And you see that the statistic in the first order does not change with time. I can tell that this property is a property of first order stationary process. But let us consider another information about the process statistics, that is a second order. What are second order statistics? Now you need to point the finger in a first time and look at all these values, that is a random variable, of course, x of t1, and point a finger in a second time, and you have another random variable, and tell me how these two random variables, x of t1 and x of t2, are related in probability. So if you have the bidimensional probability, you have the full second order statistics. However, you can just measure only some moment. For example, this is the autocorrelation, the mean value of the product of the two variables. Why the autocorrelation is important? Well, if this process in the first time and second time are very, very similar, it means that the expected value of the square difference should be very small. But as we develop this expression, we see that this is made by two terms and the autocorrelation minus the autocorrelation. It seems that if the autocorrelation is very large, then these two values are very, very similar, and we call them correlated. There is not only the autocorrelation, we should introduce other two important moments, the autocovariance, that is autocorrelation minus the mean value of the process. So this means that the autocovariance is very close to the autocorrelation, but basically the difference is that if the two samples, the two values at time t1 and time t2 are independent, for example, well, the autocorrelation will be zero. So 0 means independent, means autocorrelation is 0. If they are totally dependent, linearly dependent, the autocorrelation will be a very high number that can be either positive or negative. How much high? Well, the autocovariance does not provide you this information, but the correlation coefficient does, because the correlation coefficient is a scaled autocovariance. So this means that if the two samples read at time t1 and t2 are linearly dependent, the correlation coefficient or Pearson correlation coefficient will be either -1 or +1. 1, they are totally correlated, and -1, they are totally anti-correlated. If the Pearson correlation coefficient is 0, this means that they are incorrelated. Independent processes are incorrelated. So let us now introduce the concept of second-order stationarity. It means that the second-order statistics may depend not independently on the first time and the second time in which we point the finger, but only the distance between the two fingers, that is tau, t2 minus t1. Well, if the second-order statistics depend only on this difference, we call the process stationary in the second order. And in this case of this mathematical description we are considering, it's easy to demonstrate that the joint probability of x t1 and x t2 does not depend individually on t1 and t2, but only on the distance tau between the two samples. So the process is first order stationary, we have already assessed this, but it's also second order stationary. If it is such as first and second order, we call wide sense stationary. Now, let us see how can we estimate the autocorrelation and what are the properties. Well, the estimate of the autocorrelation for a statistical stationary process is done just by averaging the product of two samples at a distance tau. Tau is a quarter of a period on the left and half of the period on the right. And how can we do it? We average the product of the red sample and the green one, and we can do it while moving all around the time because the process is stationary. And we get numbers more or less changes, but not too much, and they are related to the theoretical value. The autocorrelation has three properties. First of all, it's symmetric. We can define it Hermitian symmetric as for minus tau, the autocorrelation is complex conjugate. Second, it's maximum in the origin. And third, the value in the origin is the second order moment, and it's always positive. Let us now make an example. We go to the roulette and we play on red and black. But we just not play once, we play a lot of time, and we want to understand the process of the accumulated won after a number of game, that is n. Let us say that W of m is the single won at the single gain m. Okay, that can be €1 or -€1 if we lose. And after n game, the accumulated won is expressed by the sum of all the won from 0 to time n. So we have a process in which each sequence of 1 is now represented as a color in this plot, and this is done by this very simple MATLAB code. So each color here represents how much we have accumulated 1 after 2, 4, 8, 10 game, and different realizations. So each realization is a color. So let us compute the statistics of this process. For example, the mean value. First of all, let us say that the single 1 can be either -€1 or +€1 with 50% of the probability. So the mean value of the single 1 is 0. But when we want to compute the mean value of the accumulated 1 after n play, we have to play with the summation, and we find that in the average, even after n1, the average is 0. And we can get from this, because if you say in any position, the average of the realization is 0. So the realizations are more or less centered about this value. They will be perfectly centered if the realization were infinite. And what about the variance? The variance can be computed by taking advantage of the fact that each 1 is independent, and so the variance of the sum is the sum of the variances. And we find out that the variance increases with the number of 1, and it is n. So as now the variance increases with the distance, and we can say that this process is not a stationary process. Let us make another case of a different process, because it is a bidimensional process. This is a random walk. It's described similar to the previous, in which I accumulate a step, but now the process has two dimensions, an x and y. This is called as drunk man walk, because it simulates the walk of a drunk man that make a step and then arbitrarily change its direction. So after any step, we have another variable that is normal, in this case, zero mean unitary variance, and after n step, we are exactly in this position. And we can compute, for example, statistics of the process. And here again, if we compute the value of this process after n step, the mean value is 0. So it means that if we say what is the most probable position in which we find the drunk man, is 0. But of course, we don't find exactly there. We find within some certain uncertainty around the 0. And this uncertainty can be modeled, for example, by the variance. And we can compute the variance exactly as we did with the previous example by summing independent steps. All the steps are unitary. If we have n step, well, now the variance will be the square root of 2n, that is 3 minus 1. In this case, we are considering a total of 1, 2, 3, 4, 5 steps. And if we do the square root of 10, we have about 3.1. This means that if we take a circle from the origin up to 0.1 for Gaussian process, this is more or less 80% of the probability to find our drunk man. And this is an example of a bidimensional process and the use of statistics.